All right, so we're in section 3.2, talking about logarithmic functions. So we talked about exponential functions the other day, and I'm just going to sketch a generic exponential function graph. Looks something like this. All right, so this graph, does this graph pass the vertical line test? Yes. Does it pass the horizontal line test? Yes. So what does that, when our function, so exponential functions pass the vertical and horizontal line test, all of our exponential functions are going to look something like that, or it's going to be a decreasing function but just reflected over the y-axis. So exponential functions pass the vertical plus the horizontal line test. What does that tell us about this function? Do you remember what that means about a function? It's one-to-one and has an inverse. So exponential functions are one-to-one. And have an inverse, or so have an inverse. One-to-one functions have inverses. And it's this inverse function that we are interested in today. So we are going to talk about this function f of x equals the log base a of x. This is going to be our inverse of our exponential function. So is the inverse of y equals a to the x. So that's our inverse function, is this logarithmic function. We call this a logarithmic function. And again, we're saying that a is greater than 0. So our base is positive. Our base is not equal to 1, because that doesn't give us very interesting function. And remember that when we form an inverse function, that the domain and the range switch. We switch the x and y values. So for our logarithmic function, x has to be greater than 0. So that becomes our domain. Remember, our range for our exponential function was y greater than 0. We had a horizontal asymptote at y equals 0. So for our logarithmic function, we have a domain restriction. So that's something we'll have to keep in mind when we work with these logarithmic functions. And because these two are inverses of each other, these are inverse functions, what we are saying is that y equals log base a of x if and only if a to the y equals x. These two equations mean exactly the same thing. Log to the base a of x is y, is the same as saying a to the y power equals x. So that's another way you can think about the logarithmic function. You can think of the logarithmic function rather than log base a. You can think of this as saying the power of a that gives me x, or the exponent on a that gives me x. The exponent on a that gives you x is y. The exponent on a that gives you x is y. That's what the logarithmic function is saying. The logarithms are exponents. And tomorrow we'll talk about what that implies about the function a little bit more. So this is how we're going to define our inverse function for the exponential function. It's the logarithm. We have these restrictions, and this is what this means. So what I want to do, we're going to take a look at a couple of examples of the relationship between the logarithm and the exponent. Talk about the graphs of exponential functions, and then we'll talk about some special logarithmic and exponential functions. All right, so questions on what we mean by our logarithmic function. Okay. So let's look at a few examples. Let's find the log base 2 of 8. So this is saying, what is the exponent on 2 that gives me 8? Or 2 to the what power gives me 8? 3, right? Because 2 to the third power equals 8. How about the log base 2 of 0.25? Let me rewrite this. Log base 2 of 0.25 is 1/4. So what is the exponent on 2 that gives me 1/4? -2. Because 2 to the -2 equals 1/4. And we talked about this yesterday, properties of exponents. 2 to the -2 is the same as 1 over 2 to the 2 power. All right, how about log base 3 of 81? This is saying what power on 3 gives me 81, or what is the exponent on 3 that gives me 81? What is it? 4, fourth power. Because 3 to the 4th equals 81. Let's do a couple more. Log base 10 of 1,000. So what power of 10 gives me 1/1000? -3. Because 10 to the -3 equals 1/1000. One a little more challenging. Log base 16 of 8. It involves a root, yes. The something over something power. Not the square root, so the square root of 8 is, the square root of 16 is an 8. Can anybody figure this one out? This is 3/4. Because 16 to the 3/4 equals 8. We take the 4th root of 16, raise it to the 3rd power, we get 8. All right, so we call what we've written in this column. This is called this. We're writing in logarithmic form. And in this column, when we rewrote it with exponents, we call this exponential form. So the two mean the same thing. They're telling us the same thing. They're just a different way of writing it. The ability to switch from logarithmic back and forth from logarithmic to exponential form is going to be a a good tool to have in this chapter. That to see how the two are related is how we're going to solve a lot of these problems. So what I want to do next is go the other direction. Go from exponential form to logarithmic form. So let's write some of these things in exponential form. And rewrite them in logarithmic form. All right, how about 8 squared equals 64? We want to rewrite that in logarithmic form. So I'll get us started. Log. What's our base? 8 of 64 equals 2. Because 8 squared equals 64. About 9 to the 3 halves equals 27. We want to rewrite that in logarithmic form. Log base 9 of 27 equals 3 halves. How about 10 to the negative third equals 0.001. Log base 10 of 0.001, we're getting the hang of it, equals negative 3. And then I'm going to do one without any numbers. The best kind of math, with no numbers. U to the V equals W. Log base U of W equals V. So this is how we translate from exponential form to logarithm. Being able to go back and forth we will need to be able to do that as we work through this chapter. And that really helps us to understand how the two are related. All right. So there are a couple of forms of logarithms that come up very frequently. So we give them special names. First, before we move on, any questions on what we did here? Are we all good with this? How the exponential and the logarithmic forms are related? Okay. Log base 10. We call the common logarithm. And we usually write the common logarithm just as log. So if we see log written without a base down here, that's telling us it's the common logarithm. It's log base 10. Because that's log base 10 comes up frequently in certain kinds of calculations. So we call it the common logarithm. So anytime you see log written with no base, it is base 10. And on your calculator, you have a button on your calculator that just says log. That is the common logarithm. We'll talk about another logarithm that we use very frequently in just a little bit. All right, so because of the way we've defined our logarithmic function as the inverse of the exponential function, and the way that relationship works, we have some properties. So properties of logarithms. We'll get into a little more detail about these properties tomorrow. Today we're just going to start talking about the properties that have to do with the logarithmic function being the inverse function, and also with how we've defined our logarithmic function. So the first one, log base a, any base of 1. What's the exponent on a that gives me 1? What power of a gives me 1? 0. Because a to the 0 equals 1 for any base. So this is true for any base. So the logarithm of any base of 1 is 0. Log base a, doesn't matter what the base is, of a. What's log base a of a going to be? 1. Because a to the 1 equals a. How about log base a of a to the x? The logarithmic function and the exponential function are inverses of each other, so what should they do to each other? Cancel out, undo each other. So this should just be x. And go the other way around, a raised to the log base a of x power is x. And we think of this as the functions undoing each other. Since they're inverse functions. Inverse functions undo each other. And then finally, if log base a of x equals log base a of y, we said that our logarithmic function was 1 to 1. So what do you think this is going to tell us? If these two things are equal, we're taking the logarithm to the same base. What does that tell us about x and y? They have to be equal. So this is one of the easier forms of logarithmic equations that we'll be able to solve. Well, part of the chapter we'll talk about solving exponential equations and logarithmic equations, and this is one technique that we can use in certain situations. So these are the properties of logarithms based on how we've defined them, how they work, and these come from them, the logarithmic and exponential function being inverses of each other. Tomorrow we'll go into a little more detail about how logarithmic functions behave. So let's look at a couple of quick examples of using these properties. Log base 5 of x equals log base 5 of 8. So x equals 8. Same base, these two are equal, so what we're plugging into the function has to be equal. So x equals 8. How about log base 5 of 1 equals x? What does x equal here? The power of 5, that gives us 1. 0. X equals 0. So a couple of easy logarithmic equations that we can solve using these properties. Questions on those problems? Okay. Usually, if we have a pretty good idea of how the exponential functions work, logarithmic functions not much more difficult. I like exponential logarithmic functions because they make you think in a little bit different way. So like trigonometric functions made you think a little differently than polynomials. These are a little different even than trigonometric functions. It's kind of a nice different way of thinking. All right, let's talk about the graphs. We know, since we know about the graphs of exponential functions, we know most of what we need to know about logarithmic functions already. First off, inverse functions, when we graph inverse functions, how are the graph of the function and the inverse function related? They reflect over, almost, y equals x. They reflect over the line y equals x. So our graph is going to be reflected over y equals x from exponential function. And because they're inverses of each other, we say we switch the domain and the range, we switch the y and the x. So all of our rules about how they graph, what was the range of the exponential function becomes the domain of the logarithmic function, etc. So all of these things come from that idea. So the domain of a logarithmic function. Our domain is 0 to infinity. And so this is saying x has to be greater than 0. So whatever we plug into our logarithmic function has to be greater than 0. Our range. The range of our logarithmic function is the domain of the exponential function. So our range is minus infinity to infinity. Because we're reflecting over the line y equals x, our x-intercept, or our y-intercept becomes an x-intercept. So we're going to have an x-intercept at 1, 0. Always. An unshifted logarithmic function is always going to go through the point 1, 0. The y-axis, our horizontal axis, our horizontal asymptote, becomes a vertical asymptote. So our y-axis is a vertical asymptote. And our function is, logarithmic function is increasing everywhere as long as our base is greater than 0. If we have a fraction as a base, our logarithmic function is going to be decreasing. Normally we work with our bases being greater than 0, normally. So our logarithmic function is an increasing function. So let's sketch a graph. Let's sketch a graph of a logarithmic function. So here are my axes sketching the graph. Generic graph of a logarithmic function is going to look like, it's going to look like this. If it's unshifted, it's going to look more or less like this, and then we can add some points to get a little more accuracy. It's always going to go through the point 1, 0. Our y-axis is going to be a vertical asymptote. It's increasing. And we're going to, for this one, let's graph y equals log base 2 of x. So now we can add some detail to our graph, plug in some points. So we're going to plug in easy points. So let's let x equal 1/2. So y equals log base 2 of 1/2. So what is the log base 2 of 1/2? -1. The power of 2 that gives me 1/2 is -1. So I get the point 1/2, -1. So here's 1/2, and I'm down here at -1. So that would be a point on my graph. We already have the point 1, 0. So our logarithmic function is always going to go through that point. It's unshifted. How about x equals 2? y equals log base 2 of 2, and I get what? The power of 2 gives me 2. 1. So my point is 2, 1. Go over 2, up 1. So that's going to be the point 2, 1. And let's pick another easy one. X equals 4. So y equal log base 2 of 4, which is, what is it? 2. So we get the point 4, 2. So we go over here, 4, up 2. So that would be a rough sketch of the graph y equals log base 2 of x. And if we look at our line y equals x here, our exponential function looks something like that. So our exponential function is a reflection over the line y equals x. So this would be y equals 2 to the x. Roughly. So questions on how we plotted that graph? Pretty easy. Once we understand how they work, when you're getting additional points, just pick nice points. Pick powers of your base, and you get nice integers. 1, 2, 3, 4, 5. All right. So transforming logarithmic functions, shifting. What do you guess I'm going to say about the shifting of logarithmic functions? Same as exponential functions, same as any other function. They shift just like any other function, but the point that's my intercept shifts along with the graph, and my vertical asymptote, if I shift left or right, is going to shift along with the graph. So that's how we're going. That's all I'm really going to say about transforming or shifting logarithmic functions. Transformations. So logarithmic functions shift just like any other graph. And our intercept, the point that's on our intercept, and our asymptote shifts along with the graph. So we can always find a point that's on our graph. We can always find our intercept by shifting our intercept and our asymptote along with the graph. So let's say our parent function, just as a couple of quick examples. Log base 10 of x is our parent function. And let's say we're going to do these transformations. So what is my transformation? What is the shift? Log base 10 of x plus 2. What does that do? How does that graph change? Left 2. So my intercept, the point that's my intercept, will shift 2 units left. My asymptote will shift 2 units left as well. How about y equals log base 10, x plus 2 minus 1. We know it's left 2. And what else happens? Down 1. So that point that's our intercept, shift left 2, down 1. And our vertical asymptote is going to shift left 2. Up and down for a vertical asymptote really doesn't matter. So, how about y equals negative log base 10 of x? What's that going to be? Reflect over the x. And so is our intercept going to change if I reflect over the x-axis? Because our intercept is an x-intercept, so it stays the same. Is our asymptote going to change if I reflect over the x-axis? No. Basically I'm flipping the graph upside down if I don't do anything else to it. And then how about y equals log base 10 of negative x? Reflect over y. So my intercept would reflect over the y-axis. My vertical asymptote wouldn't change in this case. I'm just going to reflect it over, reflect it the other way. So transformations just like any other function. We just take our intercept, point of intercept, and our asymptote along with the graph. All right, questions there? Okay. Another logarithmic function that comes up very frequently is the natural logarithm. We talked the other day, when we talked about compound interest, we had this quantity 1 plus 1 over x to the x power, and we talked about what happens as x gets very, very, very large, and we said this equal the constant e. Log base e is, we write as ln, is the natural logarithm. So when you see something like, if we're talking about y equals ln x, that's the natural logarithm of x. This is y equals log base e of x. That's what this ln means. The natural logarithm is log base e. Log base e, the natural logarithm shows up in math a lot because this quantity ends up coming up a lot in math, and it comes up in science. We use the natural logarithm quite a bit in science. We'll talk tomorrow about how we shift between bases. We can change the base of our logarithm. We can switch it back and forth. Doesn't really matter what base we use. But this one, because this quantity comes up very naturally, we call it the natural logarithm. It comes out of things like compound interest. So anytime you see ln, you should think log base e. So last thing I want to do is look at a couple of examples of using the natural logarithm, and then talk about the domain of our logarithmic function. So thinking about this, what would the natural log ln of e to the 5 be? It's going to be 5 because this is the log base e of e to the 5. Natural log and the exponential function with e as the base undo each other. They're inverses of each other, so this is going to be 5. How about e to the natural log of 3? 3. Exponential function with base e, log function base e, they undo each other, they're inverses of each other, so that's just going to be 3. One more easy example. Natural log of 1 over e squared. The power of e, that gives me 1 over e squared. What is it? Someone said it. Negative 2. This is e to the negative 2. Log base e of e to the negative 2 is negative 2. All right, questions on those? So natural log, think log base e. All right, the last thing I want to do is couple of examples of finding the domain and an intercept of a logarithmic function. So what if our problem was find the domain of natural log of x plus 3. So what did we say our domain restriction for logarithmic functions was? Whatever we plug into the function has to be what? Positive, greater than 0. So what this question is asking us is find where x plus 3 greater than 0. Whatever we plug into our function has to be greater than 0. So our domain is going to be x greater than negative 3. So the domain is always asking us, what are we plugging in here? It has to be greater than 0. If we had something really complicated, 3 minus 5 halves, 2x minus 4, 2x minus 7 times the natural log of 4x plus 3. And it wants the domain of this function. All this is asking us is there's nothing else that's going to give us a problem. I'm not dividing by 0. I'm not taking any square roots. I have to find where 4x plus 3 is greater than 0. So this is where x is greater than negative 3/4. Just solve that inequality. So questions there on the domain? And one last example. What if it said what if our problem said find the x-intercept? Of the natural log of x plus 3 minus 1. So a couple of ways we could do it. How are we going to find the x-intercept of this thing? Up 3, up, or so, down 1, left 3. So we could transform our intercept that we know our normal intercept is 1, 0. So we could apply the transformation to that. What's another way we could do it? What does y equal when we're at our x-intercept? 0. So we plug in y equals 0. So I say 0, or I'm going to go the other way around. Natural log of x plus 3 minus 1 equals 0. So I say natural log of x plus 3 equals 1. Can I rewrite this in exponential form? How do I write this in exponential form? What's our base? E. So e to the 1 equals x plus 3. X equals e minus 3. So that would be our x-intercept of this one. Solve for y equals 0. Did I do that right? Yeah? Yeah? Okay. All right, homework. All right, there you go.